perfectly fine. That's actually, I think it's very important that you actually realize that you don't know how to solve something. You know, you guys cannot imagine how glad I am when a student comes to me and say, hey, professor, I don't know how to solve this. And I asked, did you try this? He said, I tried and it didn't work. Did you try this? I tried and it didn't work. I said, that's great. So it's very important that you try things and acknowledge that, okay, I tried this doesn't work. I tried this doesn't work. This almost worked, but it seems that I need something else. What's the missing ingredient? So this is how you build up knowledge. If you sit down and try to work on a problem for a couple of hours, you know, this is how you learn mathematics. Even if you don't solve the problem, that's perfectly okay. Okay? I used to teach in high school before I was a teacher, before I did my PhD. And I used to teach middle and high school. So the youngest kids that I used to teach, they were 10 years old. I mean, did you guys ever have the experience to teach 10-year-olds in your life? Yeah. It is quite challenging, isn't it? So I had a class with 50 10-year-old students, boys and girls all over. You know, these were extra math classes, like a little bit of an invitation to prepare for math Olympiads, you know, so some extra credit mathematics. So we were supposed to do in the class, you know, slightly more advanced exercises than they would do in the regular class. Like in the regular class, the teacher teaches something and then assigns the exercise. The students have just to essentially copy and paste what they learn, you know? So in these classes, the type of problems were like, they needed to have at least one idea, you know? It was not straightforward. But sometimes they did not understand the statement of the problems, you know? So these were problems like, find all the solutions for a certain equation, x squared plus y squared equals to blah, blah, blah in integer numbers, you know? Find all solutions. And then the student would come and say, yeah, I found the solution. The solution is just the triple 1, 1, 0. And I said, you found one solution. I asked you to find all. And they would say, well, what's the difference? I said, so this is kind of very interesting because I would pose a problem to the students and give them 5 minutes to think about. And I would offer a chocolate for whoever wanted to give the solution on the board. And after 5 minutes, I would say, who wants to come to the board and show the solution of the problem? Who solved the problem? And then all the 50 students, yes, I did. So I had 50 arms raised up. Then I would pick one, and the person would come to the board, and I said, show your solution to the class. And then he would show a solution which was incomplete. Said, do you understand what this is, why this is not a solution? And I no. And then it was like this for 2 or 3 weeks. I would always offer a chocolate. Everybody would have claimed that they had solved the problem. You know, and after 3 weeks, there was a little blonde guy seated in the first row, very quiet guy. And I did the same routine. I assigned them a problem, gave them 5 minutes to think about, offered a chocolate for the solution, and asked, who wants to come to the board to show the solution? And then I had 49 arms up. I did! And only one person didn't raise the arm. And I asked the guy, you don't know how to solve this problem? And he looked to me in my face and he said, I don't know. And I said, you guys should pay attention to this guy, you know? This guy is learning mathematics. So, it was actually, this is a true story, you know? You know, this were kind of extra classes, you know, so students were not required to take this. So, of course, we start with 50, week 2 we have 40, week 3 we have 30. So the students keep going out, going out, going out. At the end of the year, there was just one guy standing, and it was that guy. And he was like multi-medalist in the competitions that he did in his future, you know. So this is kind of the learning process that I want you guys to have in mind, you know. Mathematics sometimes, the first stage is you don't know how to solve something, and you think you know. Second stage is that you don't know how to do something, but you know you don't know. And the third stage is you actually learn how to do it, okay? So please, get rid of this first stage as fast as possible. Let's just move to, you know, even if you don't know how to do something, you can acknowledge, you know, what's correct, what's wrong, and let's try in this class to keep the mistakes, keep the errors at a minimum. Of course, everybody makes mistakes when they write a solution. I make mistakes, you make mistakes. But when you write a solution, try to be as sure as possible. Yeah, this is correct, you know, because I'm following the mathematically logical steps, and this is, I truly believe that this is correct. If you are in, you know, well, I think this is correct, I'm going to write this. Maybe the professor won't see and he will give me the grade. Probably I won't see because, you know, it's kind of hard to read many essays from many students, but this is not the correct attitude, okay? All right. This was just one short story. So this is what I want for you guys to do in the homework. As a matter of fact, the homework, you see that I started with some, the type of exercises that I'm putting in this homework are just some things that I don't want to do in the class that I think you can learn by yourself and do it. If I do here, I'll take half an hour. But then you can say, well, you spent half an hour telling a story. Why can't you teach us mathematics in half an hour? I think the story is more interesting than proving that f plus g is measurable if f and g are measurable. You know, I mean, these things you can do. So there will be exercises which are kind of complementary to the class. But I did this in the homework 1, almost all the problems, and homework 2, half of the problems, but I will stop doing this, you know. I'm telling you that the things, I'm going to keep pushing you more and more. And you have to be fighting back, okay? This is like you guys are in a pool, I'm putting your head down, and you go up to breathe a little bit. I'm going to put your head down again, but keep fighting back, okay? Keep trying. This is how you learn. At the end of this class, perhaps most of you or all of you won't like me, will not want to take a class with me anymore. That's fine. But I am sure you will acknowledge that you have learned things, okay? So this is what I care. Good. All right. So let's start. I'm kidding, right? What's not to like about me? No. So we are in lecture 6 of our real analysis. By the way, reach for me if you have questions on these homeworks. Don't leave up to the very last day. You know, come to me, come to Andrea before. I have a question on this. Can I ask you something? Ask me something. Ask for a hint. Bother me. Bother Andrea, our tutor. You know, we'll try to give you some hints on how to do these problems if we know. Sometimes I put a problem in the homework that I don't know how to solve. That's perfectly fine. I want to see if some of you guys come with ideas that I don't remember how to do it. Okay? There will be problems like this too. So this is, okay, let's talk about this a little bit more on the Lebesgue measure and this so-called Littlewood's 3 principles. Okay. This is the title of the class today. We have some ground to cover. All right, 11:13. Let's see if in an hour and a half we can do our business here. So let's start with a basic review of where we are. In the last 2 classes, I hope you enjoyed, we gave this construction of the Lebesgue measure, right? So we defined, first, the exterior measure of a set, any set, as the infimum of the sum of volumes of cubes, Qj, over all collections of cubes such that their union contains my set E, right? And these Qj's are cubes, for us, closed cubes. This was the exterior measure, and it's defined for all sets. Okay, so keep that in mind. Exterior measure is defined for all the subsets of Rd. Okay, so this is for all E subsets of the Euclidean space Rd. And then we defined the Lebesgue measurable sets and the Lebesgue measure. Remember that a set E is called measurable. Lebesgue measurable is simply measurable if what? Well, we define it like this. If for any epsilon bigger than 0, there exists an open set O that contains E, such that the exterior measure of O minus E was small, bigger than epsilon. Okay? So the measurable sets are the sets that are not too crazy. Too crazy in which sense? Well, for any epsilon, there is an open set that contains it such that the exterior measure of the difference is small. Okay? This, we baptized the measurable sets, and we define in these sets, we defined the Lebesgue measure, M of E, to be just the exterior measure. Okay? And then we succeeded in the last 2 classes by proving 2 important facts. So the measurable sets are, in fact, a sigma algebra. So we proved all the properties required for it, this collection of sets to be a sigma algebra. And the second thing is that the thing we called M there, the measure, is, in fact, a measure. Okay? I ended last class with this property that I want to start today reviewing. So let me write down here. So this is, let me recall this proposition, and maybe we can discuss it a little bit. Proposition. So you may call these approximations of sets. You know, who are these sets of measurable sets? Sometimes people usually refer to this as a regularity of the Lebesgue measure, you know. Which was essentially to say the following. So let E be a measurable set. Then, for any epsilon bigger than 0, you have the following implications. So there exists an open set O that contains E such that the measure of O minus E is less than or equal than epsilon. So you can approximate by an open set from outside. Well, this is just the definition, you know. Second one, there exists a closed set F contained in E such that the measure of E minus F was less than or equal than epsilon. Now, 3 was a statement when you have 3. If M of E is finite, there exists a compact K contained in E such that the measure of E minus K is less than or equal than epsilon. And finally, number 4, I'm going to try to write here so I don't erase this. Again, if you are in the case of finite measure, I'm going to write this. There exists a finite union F, union of QJs, J's from 1 to n, of disjoint, or let's say, of almost disjoint closed cubes, almost disjoint. Okay, so you can take a finite union of almost disjoint closed cubes such that the measure of the symmetric difference is less than or equal than epsilon. Okay, and recall this just an addendum, this symmetric difference of 2 sets is just E minus F union F minus E. Why? Why do we need what? Why do we need number 4? That's a good question. Why do we need anything in life? I mean, sometimes I'm saying this in the sense that it might be useful, okay? Keep that in mind. It might be useful sometime for you. Yes, okay, so this is, you see, this will lead up to what I want to say in the class today. I think you ask me the same question at the end of the class today, if you're not satisfied, okay? Let's prove this very quickly. Let's kind of start by proving this thing. Well, I said, one is just the definition of a measurable set. Two, I told you, is the definition applied to the complement. So this is the definition applied to E complement. So you take E complement, which is a set, also a measurable set, because we proved that measurable sets form a sigma algebra. And when you apply the definition to E complement, you find an open set that contains E complement, and then you take the complement of everything. This is going to be your closed set contained in E. Well, okay, number 3 is almost a consequence of number 2. If the measure of E is finite, okay, if the measure of E is finite, you can consider the set, say, En to be E intersection Bn. So Bn is just the closed ball of radius n. Okay? So these sets En satisfy E1 contained in E2, contained in E3. They get bigger and bigger. And their limit is, of course, your E. Okay? We already know that if a sequence of sets gets bigger and bigger and you have a limiting set E, we have shown that this M of En converges to the measure of E. And this is a finite number. If this is a finite number, then you can get as close as you want. Okay, so then you can choose your N large enough such that, you know, the measure of En, of E, minus the measure of En, this is always a positive number, right? Because E is larger than everybody here, is less than epsilon over 2. Okay? But then, this is the same as saying, since the measure of En plus the measure of E minus En is equal to the measure of EE, I'm just decomposing my set E into the disjoint union of two things, so the measure adds up. So this actually, I'm saying that the measure of E minus En is less than or equal than, if I move this guy to the side, M of E minus M of En, so this is going to be less than epsilon over 2. Good. And then you're okay, because now your En now you can apply to find a closed set inside your En. You can apply to find a closed set F contained in En such that M of F En minus F is less than or equal than epsilon over 2. And what's the big deal now? Because if you apply 2, you get a closed set. But then your En, remember, it was bounded. You're just intersecting with balls. So if you have a closed and bounded set, then this guy is your compact. Okay? And the distance from En is epsilon over 2. Right? So you have here your E, you have here your En, and you have here your K. Well, this is going to be your K, right? We can call it K. K is now closed and bounded, hence compact. So this difference is less than epsilon over 2. This difference is less than epsilon over 2. Then, of course, the measure of E minus K is less than or equal than the measure of E minus En plus the measure of En minus K, which is less than or equal than epsilon. Okay, so this is how you prove 3. It's just, again, these arguments where you cover your space by balls. And number 4 is maybe, let's see how we would do 4. If the measure of E is finite, there exists a finite union of almost disjoint cubes. there. Okay, so this is how I would suggest you do this number 4. So the measure of E is the infimum of the measure of open sets that contain E. We have proved this. Okay? So then what you do is you take your E, and then you take an open set that contains it. Okay, so you can choose this open set such that the measure of O is smaller than the measure of E plus, let's say, epsilon over 2. Let's put epsilon over 2 here. Okay, so it's a guy that contains such that, I'm just applying number 1, okay? This measure is small. Now, remember that we could take any set O, and we could cover, there was the construction to cover this by an almost disjoint union of cubes, a countable one, okay? So you can take a countable, you can write your O as a union of almost disjoint cubes, but a countable union. Okay, that's fine. But again, this guy has finite measure, so you can take the truncations of these. Okay, so if you take these sets, unions of Qj, j from 1 to the n, when n goes to infinity, this set goes to your O. O has finite measure, so these sets also form an increasing sequence of sets. And we are going to use again that the measure of these guys converges to the measure of O. So therefore, you can again choose n large enough such that if you baptize this set, what did we call? F equals to the union, almost disjoint union of these cubes up to n, you have that the measure of O minus F is less than or equal than epsilon over 2. And I claim to you that this F does the job. Let's see. The claim is that this F is good. So I had my set E, I upgraded a little bit to an open set O, I covered O by cubes, and then I chose some cubes inside that almost filled my thing, Okay. Now I want to compare this collection of cubes with this original set, It's not necessarily inside E. This collection of cubes is inside O. But when you compare to E, there are pieces which it will be almost covering E, but it could have pieces outside and inside, okay? So you really have to see that E minus F is contained in O minus F. And therefore, the measure of E minus F is less than or equal than the measure of O minus F, which is less than epsilon over 2. On the other hand, F minus E is contained in O minus E, because F is contained in O. And this implies that the measure of F minus E is less than or equal than the measure of O minus E, which you assumed in the beginning it was less than epsilon over 2. And then you just add up these two things. Measure of this guy. So the measure of this symmetric difference will be less than or equal than epsilon. Okay? So this is how you prove this proposition. Keep that in mind. So in some sense, my set E, my measurable set, any measurable set is nearly an almost disjoint union of cubes. It's essentially a collection of cubes, a finite collection of cubes. Okay? If you understand this statement like this. All right. So this is still some remarks to finish what we started discussing in the last class. Let's see. The chalk here is becoming scarcer and scarcer. At least the pieces where I can write. But okay, we ended up discussing a corollary of this, right? we ended up discussing a corollary of this. Corollary 2. And the corollary was this. If I give you a set E containing RD, E measurable set, you could, if you take this piece 1 here, if you take open sets from the outside, and you take this epsilon to be 1 over n, and you keep doing this for all n's and take the intersections, okay? So let's say corollary 1, there exists a G, which is the intersection of open sets On, and from 1 to infinity, On open, such that this G is contained, this G contains E, and the measure of G minus E is 0. Okay? It's just a little set outside E, such that the measure of what's left is 0. Okay, this follows from 1 by taking epsilon equals to 1 over n. And what I'm trying to say is that my original set E differs from a set in the Borel sigma algebra, because this is a set in the Borel sigma algebra. It's the countable intersection of open sets. It's not necessarily an open set anymore. Okay, be careful. Countable intersections of open sets are not open, but it's definitely a guy in the Borel sigma algebra. What I'm saying is that my E differs from a guy in the Borel sigma algebra by something with measure 0. If you want to come from inside, you can also do that. Well, again, there exists a set that we can call F, which is the union of Fn's, and from 1 to infinity, all Fn closed, such that F is contained in E, and the measure of E minus F is 0. And this guy is another guy in the Borel sigma algebra, countable union of closed sets. It's not necessarily a closed set anymore, but it's definitely a guy in the Borel sigma algebra. And then here you look what you have written. You have written your E, if you just take a look at this part 2 especially, you have written your E as this F union this E minus F. This is a guy in the Borel sigma algebra, and this is a guy that has measure 0. So if this guy has measure 0, if you can look at this E minus F, since the measure of this guy is 0, you can cover, let's say, for each n natural number, you can take this set, which has measure 0, and cover by a little set On there is a set E minus F is contained in On, and the measure of On is less than or equal than 1 over n. So then this E minus F will be contained in the intersection of all the ONs. Okay? And definitely the measure of this intersection will be 0. And the measure of this intersection of ONs will be 0. What I'm trying to tell you is that you can write any Lebesgue measurable set as a Borel measurable set plus a subset of another Borel measurable set of measure 0. Okay? And this is the exercise that I proposed to you the week ago to do. It shows that the Lebesgue measure is the completion of the Borel measure. The Lebesgue measure is the completion of, the Borel measure. If you endow the Borel sigma algebra with this measure, the Lebesgue measure will be the completion of this measure. Okay? Is that clear? I leave as an exercise for you to think about. This is not going to be in the homework, but just for you to think about for a moment. Do you really have more sets in the Lebesgue sigma algebra than you had in the Borel sigma algebra? Can you construct me a set which is Lebesgue measurable, but it's not Borel measurable? Think about it. Okay?
Cardinality of Lebesgue measure sets is... sorry.
Yes, yes, you can argue by the cardinality, that's fine. And then you will be proving the existence of a set. But I'm wondering if you can actually put your hands and construct a set.
Can be construct here by equivalence classes. There is such method.
Yes. So think about it, you know, how to actually prove that the Borel sigma algebra of RD, if you write it like this, is contained and different from the, let's call it the Lebesgue sigma algebra of RD, like this. Think about it. What you think? Okay, I'm not saying this is easy, but just think about it. We might come back to this in the future. Okay. Now, one other observation is that, well, let's see. Maybe another observation that follows from this that might be useful too is that let's see what I want to do. Perhaps you can draw from this number 2 here another, maybe a corollary of the corollary, if you want. Let's say part 3 of the corollary is that I claim that if E is measurable, you can write it as a union from 1 to infinity of compact sets, union of Z, where Kn is compact and measure of Z is 0. Okay, so this also might be a useful way for you to think about the Lebesgue measurable sets. So it's a countable union of compact sets plus a remainder plus a set that has measure 0. And this follows from this, right? So you write your E. If I call F this union of Fn's, what this expression here says is that E is this union of Fn's plus a remainder that has measure 0. Well, there's a little bit of an adjustment to be made here because these Fn's were just closed. And I'm claiming compact there. And what do you do? Well, then you just take each Fn and intersect with the closed ball Bm. Okay, and then you make a union over N and M, which is still countable. That's fine. All right, so this might be useful. This will be useful in at least one exercise in your next homework, okay? So keep that in mind. So yeah, so maybe answering your question, Hagar, why is this useful? One application is for you to solve the exercises in the homework, okay? All right. Huh?
This doesn't mean it's useful.
Yes, yes, I know. I'm just kidding, okay? You have to understand sarcasm. But, no, but seriously speaking, this is just an attempt to better describe these sets, okay? So they're not, when somebody talks about a Lebesgue measurable set to you, it's not just crazy concept, you know? This is a very concrete thing. You can think of, oh, it's just a union of compact sets plus some remaining pieces here that have measure 0. You know, it's kind of, you have almost a structural, you know, decomposition of these sets. So it comes up really in a lot of applications in the sense that, not applications for homeworks or exam, but applications when you want to prove other results. You know, sometimes it's just enough to prove assuming that your set is a compact set, you know, and then you use this to extend to all the Lebesgue measurable sets. This is a sort of simplification that is absolutely helpful. Okay, now, let's continue our journey today because we are far from the end. But our journey today also lets us to talk about the invariances of the Lebesgue measure. This is quite interesting because, you know, remember that we defined our outer measure of a guy being just the infimum over the sums of the volumes of the cubes, where the set was contained in this union of cubes. Ruba asked me last time, can I actually take, instead of cubes, rectangles if I want? I would say yes. Try to convince yourself that the definition leads to the same number of the outer measure of E if you take the infimum over the all possible coverings by rectangles. And by a rectangle, we mean just still with the sides parallel to the axis. What if you wanted to cover by cubes whose sides are not necessarily parallel to the axis, but are in some other position, you know, like diamonds? If you look in the plane, instead of a cube being like this, a cube being rotated 90 degrees, you would get the same thing too. I mean, if you fix some sort of axis. But let's just stick with this definition here. And you get the same thing too if you cover with balls.
Professor,
Tell me.
is this somehow related to tiling the real vector space?
Yes, exactly. So for these two things that I mentioned, you know, other rectangles and cubes in a rotated position, you can essentially use the same argument that we use to cover an open set by cubes by covering these cubes in a rotated position with small cubes in the original position, you know, taking a dyadic grid. So this is how you would prove that the definitions are kind of the same. But without going that far, directly from the definition, what we can see is let's just talk about two properties today here. So first property is the obvious translation invariance of the measure, okay? So if you take a set E and you consider a set E plus V, where V is a vector in Rd, so this is the set of points x plus V, where x belongs to E. Okay, so if you take your set E and you add up according to a certain vector V, so you move your set E right here, you obviously have that the measure, so that if the set E is measurable, the set E plus V is also measurable, and the measure remains the same. You just take, even in the definition, just take everything and translate by this vector H, your cubes, your open set that contains it, and so on. Okay, so the Lebesgue measure is translation invariant. This makes sense. This is what we wanted, right? I wanted to measure a set here, but if I just moved my set, remember, if I am in 3D, I'm trying to measure a volume of water. If I just transfer my volume right here, it should be the same. I cannot create or destroy volume by just translating. Okay? How about dilations? Well, you can also do dilations. I mean, if you have a lambda parameter bigger than 0, and you consider the set lambda E as just the set lambda x, where x belongs to E, right? So this is your set E. If lambda is smaller than 1, this is going to be your set lambda E. So you're just dilating it. By dilating all the cubes, dilating all the open sets, in the definition of measurability, you can prove that the measure of the set lambda E is actually lambda to the D measure of E. And so you have this dilation invariance as well. More generally speaking, if you have, generally, and I'll leave this for you to think about a little bit because this is not entirely trivial to prove, if you have L, any sort of linear transformation, L from Rd to Rd, a linear map, if you have a linear transformation, for example, a rotation, a rotation composed with a dilation. You can dilate the different axes with different weights. Okay, so any sort of linear transformation, you would have the following two things. So E is measurable if and only if its image L of E is measurable. Okay, and also the measure of the L of E, the measure of where it's sent to, is equal to the determinant of this matrix L times the measure of E. Okay? So this is for you to think about for a moment. Think about. Different books do these things differently. Tell me, Ruba. In the first item, it's this one. I think this is okay too if the measure is infinity, right? If the measure of this set is infinity, the measure of this set is going to be infinity as well. Is that your question? I think you don't have to put the assumption that measure of E is finite in this sense. It holds also if it's infinity. That's okay.
The third equation for professor.
Go ahead.
We can use Jordan normal form. Before we find Jordan form of L. After that, we prove this theorem for Jordan series or Jordan forms.
Yes. So this is a good way to think about this. You can write your linear transformation as a composition of simpler ones. You know, you can put in the Jordan form. You can start thinking about with a rotation, with a diagonalizable thing. You know, and then you can move from there. You know, this is not completely. It's not easy, completely trivial to prove for all linear transformations. But I'll let you think about it. Maybe we can revisit this topic in a few more classes. Okay, I'll come back to this. Well, the determinant of L is essentially, if you remember calculus, you know, if you take a linear transformation, and this is the unit cube by a linear transformation is mapped into some sort of parallelepiped, right? Parallelogram, generalized parallelogram, right? You just have to say, you take the D coordinate vectors, E1, E2, E3, E4, ED, you see where they are mapped. They are mapped into D independent vectors. They span a generalized parallelogram whose volume, and we even consider here in the Riemann sense, is the determinant of the matrix, right? Yes. This is exactly what it is, you know. This is what justifies the change of variables, if you want. Whenever you change a variable, this is what justifies when you change your variables, you have to multiply by the Jacobian, right? The determinant of the transformation. This is essentially what's behind. Because integration, remember, integration is just a process where we approximate by cubes, right? And if you change your variables, if you do a linear transformation, and everything here is mapped into something here that has the volume multiplied by a certain number, so then the integral will always be multiplied by that certain number as well. Yeah. Okay. Let me move on. Let me move on. And let's talk about number 3. How would you construct a non-measurable set? This is also an interesting construction. We have constructed the Lebesgue sigma algebra. We have constructed what we call the Lebesgue measurable sets of R or of RD, the Euclidean space. And now I want to convince you that not all sets are Lebesgue measurable. So this sigma algebra is something that is not the whole collection of subsets. There is a set, there are many sets that are not Lebesgue measurable. And let's construct, there's this nice construction of an explicit example. So you can take your, so let's see if I remember. Let's see. Let's take the interval 0, 1. Okay? And again, let's take the interval 0, 1. Let's start with this. And we are going to make an equivalence relation here. So let's consider this. Let's call it E, 0, 1. We're going to make an equivalence relation in the numbers, in the real numbers between 0, 1. We're going to say that X is equivalent to Y if their difference is a rational number. Okay, so I'm going to say that two numbers are equivalent if their difference is rational. Okay? This is what we call an equivalence relation. In the sense that it verifies three basic properties. A number is equivalent to itself. If X is equivalent to Y, then Y is equivalent to X. So some sort of symmetry here, commutativity, and some transitivity. If X is equivalent to Y and Y is equivalent to Z, then X is equivalent to Z. So whenever you have a relation that satisfies these three properties, you call it an equivalence relation, and you can divide your set into the equivalence classes. So you can actually consider the equivalence classes. Okay? And you can split your set, let's say, into the union of these equivalence classes. Let's call it E alpha, where alpha belongs to a certain collection of indices, not necessarily countable. Okay? So these E alphas are the classes, the classes of equivalence. Two of these classes are either the same. So if you take two, you could, we could, yeah. Well, yeah, I could define for any real number X, the EX to be the equivalence class of X, right? So then you have so these are the numbers which are equivalent to a certain fixed number X. And then you have the following thing, either two classes EX and EY are equal, or they are disjoint. Okay? So two classes are either the same or they are disjoint. They are the same if the elements are equivalent, otherwise they are disjoint. Because if you take an element here, it differs. If you take an element that belongs to both of them, then X would have to be equivalent to Y by this property here. Then you can write your 0, 1 as a disjoint union of the equivalent classes. So you take, these two classes are either the same or disjoint. You write your interval 0, 1 as a disjoint union of all the possible equivalence classes that you have made. Okay? This already involves some non-trivial set theory for you to convince yourself in logic that this is actually possible. But once you have this, what you do is I is not countable. So what you do is that, so for each x, you have the equivalence class of x, and two classes are either the same or they are disjoint. So you consider the collection of all equivalence classes, you know? The collection of all equivalence, the collection of disjoint of all equivalence classes. You're not going to repeat them. So you consider the collection. So you're kind of partitioning your 0, 1 into certain subsets. So you consider the collection of these subsets. This is what I'm trying to say here. And then once you have, you know, split your interval 0, 1 into this joint collection of the equivalence classes, what you do is that for each class E alpha in this thing here, you take an element, you know, you pick an element x alpha. For each class, you pick a number. You pick an element x alpha that belongs to this class, E alpha. I shouldn't have used the same, this E alpha is, well, yeah, okay, so this maybe it's the same there. And my claim is that this set J, which is just the collection of all these elements, x alpha, where the collection of elements that you chose, okay, this is not measurable. Okay, so what you're doing is that imagine yourself that for each class, for each equivalence class, you're picking one element. So you pick one element. You will not pick another element which is in the same equivalence class of that guy. Okay, for each equivalence class, you pick one element. That's fine. This involves the so-called axiom of choice. Okay, so this involves, you should take a look and read about this. Axiom of choice. And my claim is that this set that you form, let's say, with one element from each equivalence class is not a measurable set. It's not Lebesgue measurable. Okay? And let's see. Okay? All of these elements are between 0 and 1. How would we argue that this is not a measurable set? I wanted to see the following. I want to, let's say, what we are going to do is that we are going to enumerate the rationals in the interval 0, 1, okay? So let's just call this set X to be 0, 1, intersection the rational numbers, and we can enumerate this thing. So rational 1, 2. So this is a countable thing. So the claim is
we consider J plus RA. J plus
this
set is
X.
contained in -1 to 2.
Yes.
From -1 to 2.
So you consider this set J plus X, which is just the sum of elements in J plus the elements of X. Okay? So by construction, this is contained in the interval.
0 from 0 to 3.
Every element in
from 0.
This is what I want to do, or maybe I want to enumerate the intervals let me see. So let me just let me enumerate the interval, the rationals between -1 and 1. See if this is what I want to do. So if I consider J plus X in this form, this will be contained in the interval -1. Let's see if it makes a difference. -1 and So the smallest element of j would be 0. The smallest element of x would be -1, so this is -1. And on the other side, you have 2. This is definitely contained here, -1, 2. Is that okay? And the claim is that this set, j plus x, which is remember, this is the sum of elements of j with elements of x. It contains the interval 0, 1. This is the thing that you should pay attention. Okay? So this is the nice thing. In fact, you know, every element in 0, 1, every number in 0, 1, belongs to one of these classes. Okay? So if you take a generic element x belonging to 0, 1, it belongs to one of these classes. Let's say x belongs to the class E alpha. This class E alpha are the sets, the numbers were equivalent to x. You picked one. You picked x alpha. It could be that your x alpha was equal to this x, but it could be that it was just another number in the class. But when you pick this x alpha, what you guarantee is this x minus x alpha is a rational number. And since x is in 0, 1 and x alpha is in 0, 1, this rational number here is something between -1 and 1. You're taking a number in 0, 1, subtracting another number in 0, 1, you get a rational number that belongs to the interval -1, 1. So it belongs to this set that you call x. Okay? So this is because then your x is x alpha plus r. So any number in 0, 1, you really can write as a guy in j plus a guy in this x. So this contains the interval 0, 1. Okay? So this is the catch. Now, hello, who has the microphone open? Please close it. Huh? All right, sorry. So the thing is, so this j plus x is just the set of elements of I don't know. This is just the union of the sets j plus Rn where Rn goes from 1 to infinity, right? So I'm adding the elements. This is the set of j plus R, j belonging to j, R belonging to x. This is just, since x is countable, this is just the union of j plus each guy. Okay? And now this is where where you get if j were measurable, okay? If j were measurable, this set, the measure of j plus Rn would be equal to the measure of j, because the Lebesgue measure is translation invariant. On the other hand, observe that this union here, this is disjoint. This is disjoint. In fact, if you had j plus a certain rational number n equals to this, or intersection j plus another rational number m to contain an element, say, x in this intersection of these two sets, okay? It means that this x would have to be an x alpha belonging to j plus this Rn, and would be another x beta belonging to j plus this Rm. But then, this would imply that x alpha minus x beta is equal to Rn plus Rm minus Rn. This is rational. So the difference between x alpha and x beta is rational. So the two of them are equivalent. So they must be the same guy, because you're just picking one guy from each equivalence class. So this would have to be 0. And then the rational numbers, this would have to be 0 as well. Okay? So you cannot have, for different N and M for different two guys, the set J plus Rn intersecting the set J plus Rm. So this is a disjoint union. Okay? So then you would have, by the countable additivity of the Lebesgue measure, right? You're writing this set as the union of a countable union of disjoint sets. This would be just the sum from n from 1 to infinity of the measure of J plus Rn, which is just the sum from n equals 1 to infinity of the measure of J. Right? Remember, here you have no n anymore. So you're summing from 1 to infinity a certain number. And the contradiction is here, because if the measure of J, of this set were 0, then this implies that the measure of J plus X would be 0, right? You're summing a bunch of zeros. That's fine. But if the measure of this J were something bigger than 0, then this measure of J plus X would be actually infinity, because you would be summing a certain positive quantity infinitely many times. And this is in direct contradiction with this fact here. Because from this fact, the measure of J plus X, but remember that the measure of this set J plus X was something, since this set is contained in this minus 1, 2, and contains this set, the measure is monotone, right? So this measure of this guy has to be less than 3 and bigger or equal than 1. So these possibilities contradict this guy. Okay, so this is actually a contradiction. All right? So this is an example of a set that is not measurable. Well, you have to accept some pretty subtle stuff here in set theory. So read about a little bit the axiom of choice, how you can do the partition of a set into its equivalence classes and so on. So take a little bit of reading on this to make sure that, that you are okay with that. So these are kind of equivalent things of the well-ordering principle, Zorn's lemma. There are some mathematicians that don't like to use these things and actually don't believe. It's kind of a, but this is fine. Well, I believe in those things, so to me that's okay. Okay? So this is one way to construct a set that's not measurable. Okay, so let's move on to the final part of the class today, which was actually what I intended as the title. So all of this was a bit of a detour to review and do some properties of the Lebesgue measure. But this fourth part is what I called in the beginning, well, not me, this is from Stein's book, Littlewood's 3 principles on the Lebesgue measure, you know. And this is essentially a way, since we are moving from the world that we know, from the world that we were all comfortable in our undergrads, where we were learning about continuous functions, integration, calculus, you know, very concrete things, to this new world that seems a little bit more abstract. So this is just a way to keep in mind that these new concepts are not that far from the old ones, okay? In terms of comparing with things that you know. The sets, the measurable sets, are essentially cubes, or things that you know, unions of cubes. We have seen this. The measurable functions, who are these things? You say that it is essentially a continuous function. And a sequence of converging functions that converges to somebody, it will be essentially a uniform converging sequence. So these are the 3 principles that I wanted to discuss. So every set every set is nearly a disjoint union of cubes nearly, every function, every measurable function is nearly continuous and again, every convergent sequence of functions is nearly uniformly convergent. And I put in quotes here these words nearly, because this is what we have to better explain, okay? But these are the moral principles that we should have in mind. Every set is nearly a disjoint union of cubes. So when I say here, I say every measurable set, okay? Every measurable set is nearly a disjoint union of cubes. Every measurable function is nearly a continuous function. And every convergent sequence of measurable functions is nearly a uniformly convergent sequence of functions, okay? So these are theorems that have their own names, and we're going to discuss each of these, okay? So in fact, I regard this number one as we already proved. So the understanding of this number one is actually the understanding of the proposition that was right here, that you thought, what's the importance of this? So it's essentially, this is what we had in our proposition 1 of the class today, the item 4. We proved that every set was nearly a disjoint union of cubes in that sense. Given epsilon, you can find a disjoint union of cubes such that the measure of the symmetric difference was less than epsilon. So let's discuss now these propositions 2 and 3. Tell me.
Losing.
Yes.
Theorem losing.
Let's discuss these two theorems, which will carry the names of Egorov's theorem and Lusin's theorem.
Russian mathematicians.
Russian mathematicians, right? You are from Kazakhstan, aren't you?
What?
Where are you from?
Uzbekistan.
Uzbekistan, I'm sorry. Yes. So I'm very good when somebody gives me right feedback on the history of mathematics. This is all something, well, I should know more, and we all should know more about the history of mathematicians. So yes. Let's see. Okay, so we have a few minutes. Let me try to finish this today. Okay, so we have a few theorems to prove. Let's see. What do I want to do? Okay, so I want to prove this theorem which is Egorov's theorem. This is theorem number, well, I lost the count here. But the thing is, okay, so let E contained in Rd be a measurable set with M of E being less than infinity. Okay. Let Fk, k bigger or equal than 1, be a sequence of measurable functions defined on E such that Fk converges to F almost everywhere. When I say almost everywhere now, I am of course referring to the Lebesgue measure. So almost everywhere on E. So the claim is, given epsilon bigger than 0, there exists a closed set f epsilon contained in E such that the measure of E minus this f epsilon is less than or equal than epsilon, and fk converges to f uniformly on this f epsilon. Okay, so let's try to prove this. I'm saying is that if you give me a set, any measurable set of finite measure, okay, so this is going to be important. Give me any measurable set of finite measure. Let fk be a sequence of measurable functions, such defined on this set. Okay. By the way, we have defined everything in RD, okay? But sometimes we're going to work with subsets of RD. That's perfectly okay if you want to work with functions defined on a set E. What you do is you take all the sigma algebra of Lebesgue measurable sets in RD and you intersect with E. This forms a sigma algebra of subsets of E. Okay? This is usually what we are referring to. So you give me a sequence of measurable functions defined on E such that fk converges to f pointwise almost everywhere on the set E. The claim is that given any epsilon bigger than 0, you can find a closed set in E such that the measure of the difference is small, smaller than epsilon, and the convergence becomes uniform when restricted to this set. Okay, so this is kind of trying to give meaning to that principle number 3 there. Every convergent sequence is nearly uniformly convergent. All right. Let's see. So proof. Let's try to prove this. Proof. So first of all, let's assume, we may assume that fk converges to f everywhere in E, okay? Why can we do that? Well, I'm assuming that the convergence takes place almost everywhere. So the set where the convergence does not happen, call it N, is a null set, is a set of measure 0. So instead of working on E, you could work on E minus this set. Okay? So just replace E by E minus the set where the convergence does not happen and try to prove the result. All right, so let's assume that the convergence happens everywhere. Now, let's see. For each n bigger or equal than 1 and k bigger or equal than 1, let us define the following sets. Let's define E and k as being the set of points x in E such that fj of x minus f of x is less than or equal than 1 over n for all j's bigger or equal than k. Okay? So let's define this set. Let's take a moment to reflect on what it means. Set of points x in E such that the difference fj minus f at the point x is less than 1 over n for all j's bigger or equal than k. Okay, so now observe that for each fixed n, you have the following things. You have that E and k. So if this thing holds for all j bigger or equal than k, it certainly holds for every j bigger or equal than k plus 1. So this set is contained in the E and k plus 1. which is contained in the E and K plus 2, and so on. So this is an increasing sequence of sets. Moreover, the union over K of this E and K's is what?
Decreasing sequence with respect to n.
This is going to be the whole set E, right? Let's see. This is an increasing sequence, and I claim that the union of these things, let's say K from 1 to infinity, is going to be the whole set E. Why is that?
A in n.
I am assuming that the convergence takes place everywhere in E. Okay, so if you give me a point x in E, this means that fj of x will converge to f of x. Since n is fixed, for some large j, fj of x minus f of x will be less than or equal than 1 over n, and this particular point x will belong to this E and K up to that point. Okay, so any point in E will belong to a guy here for K sufficiently large. So great. What do we know about sequences like this? And I'm using, perhaps for the third class today, the very basic fact that if you have an increasing sequence of subsets, converge, and the union is this, the measure of these guys converges to the measure of the union. Right? So you say, from this, you get that the measure of these EKNs converges when K goes to infinity to the measure of E. Okay? All right. Now what do I want to do? Well, now it's the point where it's important to use this hypothesis here, where the measure of E is finite. Okay? Where the measure of E is finite. Why? Well, then I have a finite number here. I have a sequence of numbers converging to this finite number, so I can get them as close as possible, right? So in other words, if I give you epsilon, you can find, so my claim is that you can find, remember, n is fixed, okay? N is fixed. You can find K of n, let's call it Kn, such that the measure of E minus the measure of this En Kn will be less than or equal than epsilon. So given any epsilon, we can put this less than this. So let's actually just put epsilon, let's say 1 over 2 to the n. Let's choose this epsilon. Okay? So this number converges to E. There is a K sufficiently large that we call Kn, such that the measure of E minus the measure of En Kn is less than 1 over 2 to the n. All right? Then what do we do with these things? What do we do is we note, note that you have your E is just E minus this En Kn union this En Kn. This is a set that is inside your E. So you're writing your E as the disjoint union of two things. Okay? So then the measure of E is just equal to the measure of this difference plus the measure of this guy. You move this to the left, and you conclude that the measure of the difference, E minus En Kn, is less than or equal than 1 over 2 to the n, okay? Because the measure of the difference is just the difference of the measures of these two guys, and this is less than 1 over 2 to the n. You could not have done this if the measure of E were infinity, okay? You cannot you cannot say you're getting as close as you want to infinities in the sense that the difference is less than some number. So this is where it's important to use that the measure is finite. All right, so we're almost there. So we have constructed, for each fixed n, a certain set which we call En Kn, such with this properties there. So now the idea now is to take a big N. Remember, you're in the very beginning. You're given this epsilon here. Okay. So take a big N, take n large, such that, let's try to do such that you have that the sum over 1 over 2 to the n, for n bigger or equal than this big N, is less than, let's say, epsilon over 2. Let me just write this here. Sum over 1 over 2 to the n for n bigger or equal than n, less than or equal than epsilon over 2. You can certainly do that, right? So you're given epsilon in the beginning, choose a big N sufficiently large such that the sum of the inverse powers of 2 is smaller than epsilon over 2. And then you will consider the set. Let's see what we want. We will consider the set A epsilon to be just the intersection of all of these En, Kn with n bigger or equal than big N. Let's consider this. And my claim, so these were the good sets, good in the sense that Fj was very close to F in this set, and I'm taking an intersection. So intersection of good sets, so a guy that belongs to this intersection will be a point, X, in which Fj will be very close to F, for all n. So these will be the points where the convergence is going to be uniform. So my claim to you is that Fj converges to F uniformly on this set AE, A epsilon. Let's try to prove that. Okay? Remember what it means to converge, what it means for a sequence of functions to converge uniformly. Right? You know that Fj of x will converge to F of x, meaning that given delta bigger than 0, there exists a J0 such that if j bigger than j0, you have Fj of x minus f of x smaller than delta. This is the definition of pointwise convergence. Fj of x will converge to f of x if given delta bigger than 0, there is a j0 such that if your index j is bigger or equal than this index j0, then Fj of x minus f of x will be less than delta. Uniform convergence means that this will be true, the same, given delta, the same j0 will work for all the x. Okay? It will work for all the points. This is what we have to do here. So let's do it. So let x belong to A epsilon, given delta bigger than 0. So given a delta bigger than 0, what you can do is that choose an M, choose an M such that such that 1 over m is less than delta. Okay? And you can actually choose this m bigger or equal than this big N that you chose there. The big N was already chosen. It's fixed. It's right here. Okay? So now I take a point in A epsilon, and I give you a delta bigger than 0. You can choose a number m bigger or equal than n, and such that 1 over m is less than delta. Okay? Now, remember, this A epsilon is the intersection of a bunch of stuff. So this means that your point x belongs to this intersection will belong to the set which we call E, M, K, M. Okay? Because M is bigger or equal than this big N. And if your x belongs to this set, this means that fj of x minus f of x, okay, is less than or equal than, by definition, 1 over m, which is less than delta, for all j bigger or equal than this km. Okay? And the thing is, this statement here is just independent of the x that you chose. So give me any point x in AE. In fact, x is just a point in AE that is contained in this set. So every point in A epsilon is contained in this set here. This means that this inequality holds independent of the point that you chose in A epsilon. Okay? So this actually means that this choice of J0 works for all the points x in this set A epsilon. Okay? Hence, the convergence is uniform there. We're almost done. So to finalize, just note that this set here is very close. Each of these sets, E, N, K, N, was very close to being E. Very close. Okay? So you expect that the intersection of some of things that are very close to being E is still very close to being E. And this is actually true. You know, this E minus AE. What is that? Let's take a look at what this is. This is E intersection A epsilon complement. This is E intersection a bunch of guys here. Okay, and complement, which is just E intersection the unions of this E, A, K, N complement. Well, what I want to do is I claim to you that this is contained in the union of E minus E, N, K, N. N is bigger or equal than N. Okay? This is when N is bigger or equal than N. This is when N is bigger or equal than N. Okay, so N, a set E, intersection a union, will be the union of, yeah, because the set must be E, it must be one of these guys. Yes, so it's going to be, this is, I wanted to convince you that this is an equality or an inequality. So maybe I just wanted to, maybe I'm just overcomplicating here. Of course, everything that I wrote here is correct, but I think I'm just overcomplicated. So I just want to claim to you that this set is contained in the union, when A is bigger or equal than N, of E minus each of these E, N, K, N's. And the reason is, let's say, if a point is on this side, that must be because it belongs to E, and it does not belong to the intersection of all these things. Okay? So if it does not belong to the intersection of all of these things, there must be at least one guy such that the point does not belong to that guy. Okay? And here is, there will be one guy such that the point does not belong to this guy, but it belongs to E, so it will belong to E minus this thing. Okay? Then from this, what you get is that the measure of E minus the set A epsilon is less than or equal than the sum of the measures of E minus E n k n, when n is bigger or equal than n. And remember, this was chosen to be less than 1 over 2 to the n. So this now justifies our choices, you know. This is less than 1 over 2 to the n, and we chose the big N such that this was less than or equal than epsilon over 2. Okay. I hope I made my point clear. So if these are sets which are very close to E, their intersection is still very close to E in the sense that the measure of E minus A epsilon loses to epsilon over 2, according to our choices. And you're almost there. Let's see. I was able to produce a set, A epsilon, lying inside E, such that the convergence was uniform there. The measure of E minus this set was small. What I'm missing is just this closed thing. My set A that I produced here is not necessarily closed, but who cares? We already know that any set can be approximated from inside by a closed set, by the regularity of the Lebesgue measure. So the final step is to just, okay, so now just choose your F epsilon inside your A epsilon, F epsilon closed, and such that the measure of A epsilon minus F epsilon is also less than or equal than epsilon over 2. Okay? So you had here your set E, you have your set A epsilon inside, the difference is the measure of the difference is less than epsilon over 2, and you're choosing now a closed set F epsilon inside A epsilon, whose difference is also less than or equal than epsilon over 2. So if you add this up, the measure of E minus F epsilon is less than or equal than epsilon as desired. Okay? All right. So I guess we are almost on time today. We started a little bit late. But I don't think I'll do today the other theorem. So let's leave it for the next class. So we proved today this. We understood 2 of Littlewood's principles, like that every set is essentially a finite disjoint union of cubes. And we proved now that every convergent sequence of functions is essentially uniformly convergent, in the sense that described here by Egorov's theorem. In the next class, we will start by doing the 3rd principle that we left here, that every function is essentially continuous. This is going to be Lusin's theorem. Okay? And maybe we start discussing a little bit more about LP spaces in the next class. All right, so let's finish here today. You have a few more days to work on this homework, and I'm going to assign to you the next one today, this afternoon, so you can start taking a look too. Work together, talk to your friends, talk to me, talk to our tutor, and solve these problems, and write down your solutions, okay? Bye-bye, you guys who are watching at home. Have a good weekend, and keep in touch, okay? Let's finish here today.
Thank you.